Hello everyone, welcome to Neso Academy. In the previous lecture, we started scalar data types and covered integer, natural, boolean, real, bit and physical types. Now, for digital signals, we used bit data type, zeros and ones. But in real hardware design, zeros and ones are not sufficient. We need some more values. For that, we use standard logic types and enumerated types, which are our remaining two scalar data types. Therefore, the name of the lecture is Scalar Data Types Part 2. In this lecture, we will understand the remaining two scalar data types. So, let's start the lecture. In the previous lecture, we understood the definition for data types, where data types define the set of values a data object can store. And data types are broadly classified into scalar and composite types. We also saw that scalar data types are mainly classified into 8 types, from which we have already covered the 6 basic types. Now let's understand the remaining 2 standard logic types and enumerated types. Let's start with the 7th standard logic types. Standard logic types are defined in IEEE 1164 standard. Means IEEE 1164 standard officially provides and defines standard logic data types for VHDL. Means standard logic types follow the rules created by IEEE 1164 standard. And in IEEE 1164 standard, standard logic is mainly classified into standard underscore logic, which is resolved type, and standard underscore U logic, which is of an unresolved type. Let's understand each of them. The first, standard underscore logic. Standard underscore logic can take inputs from multiple sources and determine the final value on its own. That is, standard logic can take inputs from multiple sources. Means a single signal can be connected to more than one source, and standard logic will determine the final value on its own. Mean if multiple sources try to give different values, then standard logic will act as a resolver to decide the final output from multiple values. Therefore, standard underscore logic is called as resolved type. To make it more clear, let's take an example. Consider a VHDL code where I am assigning a signal named A equals to 1. Now, in the same code, if I assign the same signal A equals to 0, now what will A hold? 0, 1 or something else. Here, standard logic will check all the incoming values and decide the final value. In this scenario, A will hold X, means unknown, which represents a conflict between 0 and 1. While standard U logic allows only a single source for a signal. In the same example, if I assign signal A equals to 1 and again signal A equals to 0, for standard U logic, it will generate an error because standard U logic cannot resolve multiple sources. Therefore, it is called as unresolved type. So, I hope you understand the difference between standard logic, resolved type, and standard U logic, which is an unresolved type. Let's see the next point. Standard logic type supports 9 distinct values and is used in real hardware design. Means, in real hardware design, do signals always have only zeros and ones? No. Signals can be anything, an unknown value or an open circuit. So zeros and ones are not enough. Therefore, we use standard logic because standard logic type supports 9 distinct values, and 9 distinct values are U, X, 0, 1, Z, L, H, W, and hyphen. Let's understand each of them. The very first, U, means uninitialized. Default value at the start of the simulation. Uninitialized means signal has not been assigned any value yet. It represents the start of the simulation where VHDL does not know the value. Next, X, which is forcing unknown, indicates conflicts between two drivers. Drivers means sources. Forcing unknown means final value cannot be determined. Just like we saw, if one source says assign value 1 and another source say assign value 0, in that scenario, output will remain unknown, which represents a conflict between two sources. Next, 0, which is forcing low or strong logic 0. 0 represents binary 0. Next, we have 1, which is forcing high or strong logic 1. 1 represents strong binary 1. Next value, Z, which is high impedance and open circuit. High impedance means signal is disconnected, which represents an open circuit. Next value, L, which is weak low. Weak version of logic 0. Weak low means almost binary 0. In terms of physical electricity, if logic 0 represents a signal directly connected with a ground, means 0 voltage, then weak low will represent a signal connected with a ground using a resistor. Now here, there will be a voltage drop across the resistor. So, weak low will almost be logic 0, but not exactly, such as weak low will be 0.3 to 0.5 volt, but not exactly 0 volt. Next, H, which is weak high. Weak version of logic 1, almost logic 1. Now, in terms of physical electricity, if 1 represents a signal directly connected with a voltage supply, then weak high will represent a signal connected with a voltage supply using a resistor. Not exactly 1, but weak 1. Next, we have weak unknown. W represents a conflict between two weak sources. Means weak unknown represents conflict between weak low and weak high. Just like X represents a conflict between strong 0 and strong 1. In the last, we have hyphen means don't care. The value can be 0 or 1. Means any value, either 0 or 1, is acceptable. To understand this don't care, consider an example. If I want to stop the simulation of hardware whenever the 2-bit input starts with binary 1, means when input values are 10 and 11, then stop the simulation. In that scenario, I will use don't care. How? Using if input is 1, don't care, means input is 10 or 11, then stop the simulation. So, this will save simulation time and it will save the extra usage of logic gates inside the hardware. So, I hope you understand these 9 distinct values. Let's take few examples. Here, I am declaring a signal named A with a data type standard logic using the keyword standard logic. Now, in this case, I have not assigned any value, means this signal A can take any of these values, or we can directly assign a fixed value. Example, I am assigning logic high to this signal A. Or we can directly use signal assignment operator. Here, I am using signal assignment operator to assign logic high to this signal A. Now, what if I assign logic 0 to this same signal A? What will A hold? For standard logic, A will be X. But in case of standard U logic, it will generate an error. So, I hope you understand standard logic types. Let's see the last one, enumerated types. Enumerated type is a user-defined data type that consists of a set of named values. Means, an enumerated type is a custom data type that consists of a set of named values. Named values means we use names instead of integers. Now, what if I want to represent states like colors? Example, red, yellow, green. Can I use an integer data type? No. Can I use a bit data type? No. So, what we do? Here we create a custom data type. Let's see how. Using the keyword type. Type is a VHDL keyword that is used to create custom data type. Here I am creating a custom data type traffic_light. Keyword is used to start the body. Inside the parenthesis, mention the elements that you want to store inside this data type. Example, red, yellow, green. So here I have created a custom data type traffic light which stores red, yellow, green. Now how to use this data type? Just like we used others. So here I am declaring a signal named light with a data type traffic_light. Means this signal light can store any of these names, red, yellow or green, but not any other colors. So I hope you understand how to create a custom data type. Now custom data type makes the code more readable and more meaningful, which means we are done with this enumerated types. So we are done with this topic, scalar data types. In the next lecture, we will study more about composite data types in details, which means we are done with this lecture. I will see you in the next one. Thank you.